In the 1970s, astronomers discovered that our Milky Way galaxy is moving. Drawn by great invisible forces, we were being pulled towards something, but we couldn't see what. Our final destination was hidden by the zone of avoidance, a region of the sky obscured by the gas and dust of the galactic disk. Like a tiny raft adrift in a vast ocean on a moonless night, we were caught up in the current, heading towards who knows where. And we weren't alone, for it wasn't just the Milky Way that was in motion, but all of our neighbors. Two astronomers, R. Brent Tully and J. Richard Fisher, were using the Parkes Radio Telescope in Australia to conduct a survey of distant galaxies, attempting with their meager observations to reconstruct their movements. And around the same time, multiple teams of astronomers were observing the cosmic microwave background, the bath of radiation that survives as a relic from the early days of the Big Bang. And independently, both groups found the first hints of this great cosmic flow. The galaxies that Tully and Fisher mapped seemed to share a common locus, their reconstructed velocities all roughly pointing in the same direction. As for the cosmic microwave background, its temperature across the sky revealed a bias. It was slightly hotter in one direction and slightly cooler in the other. Much of this discrepancy could be eliminated by considering the motion of the Sun around the core of the Milky Way. But even after that subtraction, a residue remained, an unexplained source of motion relative to the ultimate cosmic reference frame, a speed amounting to hundreds of kilometers per second. It appeared as if the Milky Way and all the other galaxies in our nearby vicinity of the cosmos were being drawn to a particular spot, a specific location in the universe, as if tied by great invisible chains stretching tens of millions of light years. We couldn't see it, couldn't map it, couldn't figure out what it was. For decades, the best we could do was simply name it. The Great Attractor. A great source of inexorable motion, a persistent sink of gravity, a single point in the cosmos that pulls and pulls and pulls. Our entire galaxy and thousands of others, home to hundreds of billions of stars and countless planets, drawn to the Great Attractor like helpless moths to a flame. And yet, no matter how odd this may seem, this is not an unusual situation in the cosmos. For the universe is far from static. Every object within the universe is in a state of restless motion, from the orbit of the Earth around the Sun to the Sun's drift within our galaxy, to the hurtling of the Milky Way towards the Great Attractor. And that's not even the largest example in the universe, for the Great Attractor turned out to be just the tip of a far grander cosmic iceberg flowing across the sky. Vast cosmic structures and motions dwarfing anything we had ever seen before. And so, nothing is still. Everything is going somewhere. The question is, where? On the 23rd of September 1999, the Mars Climate Orbiter lost contact with NASA as it approached the planet. The mission was totally lost, and it later turned out to have been down to a mistake converting metric to imperial units. Even multi-billion-pound projects that are supposed to work seamlessly can fail, and that can also be incredibly frustrating when it comes to stuff you use every day, which is why our sponsor today, Raycon, are a great choice with their everyday earbuds. They are very reliable, with a 32-hour battery life, multi-point connectivity to join with 2 devices at once, and brand new active noise cancellation, so you can even enjoy History of the Universe on long flights without trouble. They've also been great for editing the audio for the videos too. They're comfortable to wear for long periods of time, which is especially important deep into the edit when I'm wearing them all day long, and the quality rivals some of the big names in audio for almost half the price. The protective case cover is also a great, stylish bonus and especially useful for me as I'm always losing earbuds, and it supports wireless charging. So head over to buyraycon.com/HOTU today to get 20 to 50% off site-wide. Thanks to Raycon for supporting educational content on YouTube. Our universe is defined by motion, and one way to describe the history of science is through our increasing awareness of the restlessness of the cosmos. For millennia, the brightest scientific minds in Europe and the Middle East believed that the Earth was perfectly still and that the heavens revolved around it. Those early astronomers busied themselves with attempts to explain and predict the motion of other objects: the Sun, the Moon, each of the known planets, and the stars, and their predictions worked surprisingly well. But their cosmological system of motion wasn't perfect. In fact, it was an ungainly mathematical mess, relying on small circular orbits nested within larger ones, with some centered on the Earth and some centered on other points. And so, on his deathbed in 1543, the Polish astronomer Nicolaus Copernicus published On the Revolutions of the Heavenly Spheres, a radical reformulation of the old system that put the Sun at the center of the universe, still and motionless, with the Earth set in motion around it, along with all the other planets. Reaction to the work of Copernicus was mixed. On one hand, it was a bold reshaping of the universe. On the other, it was arguably just as messy as the ancient system it was trying to replace. And on top of this, it introduced more than a few questions that had no easy answers. First and foremost, if the Earth was moving, how could we tell? We know we are moving on the surface of the Earth through a variety of ways. We can feel the wind against our face when we run, or watch as a distant goal draws nearer. So why don't we feel a great rush of wind as the Earth orbits around the Sun? Or why aren't we flung off into the void of space due to the incredible rotation of our planet? It took centuries of science and the development of Isaac Newton's theory of gravity for the full picture to come together. Today we know that we don't feel the motion of the Earth because we are in motion along with it. And since the vacuum of space is just that, a vacuum, there's nothing for us to push against and betray that motion. And so how can we guarantee that the Earth truly is in motion? Is there a standard reference? Indeed, Newton assumed that such a standard existed, that there was a fixed frame of universal reference from which all motion could be measured. In crafting relativity, Einstein rejected the concept of a fixed universal ruler against which we could judge all motion. Instead, all inertial motion was relative. The only way to measure motion is in reference to something else. And from this fundamental idea, the rest of relativity blossoms. The fabric of space-time, the equivalence of mass and energy, the limitations of the speed of light, all of it. Imagine cruising in an unpowered rocket ship and encountering your friend doing the same in the opposite direction. You are both in an inertial frame of reference, moving at a fixed speed. As you cross paths, you may declare that you are moving and they are staying put. But in relativity, they have just as equal right to state that they are moving, and you are the one that is standing still. These two perspectives are equally valid. Despite this, we can tell that the Earth is spinning because of the Coriolis force, which twists airstreams around to form hurricanes and typhoons. And so even if our skies were completely blank, with not a single star to be seen in the sky, with nothing left to measure except what we have right in front of us, we could still deduce the motion of the rotation of the Earth. But the movement of the Earth throughout the greater universe is another matter altogether. For that, we need to identify some other frame of reference, some other yardstick for us to measure from. Otherwise, we could rightfully claim, just like any other object in the universe, that we are motionless, and that the rest of the cosmos, every planet and star and galaxy, moves around and about us. And thankfully, the universe itself gives us exactly the tools we need. The trick is that we don't live in a static universe, but an expanding one. The cosmos changes from day to day. In the past it was smaller, and in the future it will be larger. And it is this that allows us to write down a preferred frame of reference, one that expands along with the universe, allowing us to measure motion relative to that. In other words, at large scales, the universe is expanding. On average, galaxies are getting farther away from each other with time. We can then define motion on top of that general expansion. Anything that deviates from the general outward flow of the universe is special and unique. In the parlance of cosmology, this is known as peculiar velocity, and these velocities can range from a few hundred to a few thousand kilometers per second. And armed with this mathematical toolkit, cosmologists can begin to understand not just the rotation of the Earth or the orbit of our planet around the Sun, but the movement of our solar system within the galaxy and the action of the Milky Way within the wider universe. And so without even feeling it, without even taking a single step, you will move an incredible distance through your life. First, there is the rotation of the Earth. Depending on where you sit on the globe, you could be whipping around at up to 1,600 kilometers every hour. Of course, if you happen to be standing on either geographic pole, your rotational velocity will be exactly zero. For most of humanity, which lives somewhere in the mid-latitudes between the poles and the equator, the typical everyday velocity is around 1,000 kilometers per hour. For a typical human lifetime of around 80 years, or 700,000 hours, that gives a lifetime movement of around 1 billion kilometers, just due to the rotation of the Earth. But the Earth is also orbiting the Sun with an average speed of 30 kilometers per second. Over your lifetime, that adds up to around another 80 billion kilometers of total movement, though of course most of that is in a rough circle, so it's not like you're going anywhere with it. And the orbit of the Earth is not the end of our motion. The Sun, along with all the planets, asteroids, comets, and all the other denizens of the solar system, moves within the Milky Way. Most of that motion is a simple orbit around the galactic center, a journey that takes 230 million years to complete a single revolution. But in that time, the Sun travels an enormous distance, giving it an average speed of around 230 kilometers per second. And interestingly, that number is also profound evidence for the existence of dark matter within the Milky Way. When we add up the mass of all the luminous objects within the orbit of the Sun, even including generous allowances for all the stars and clumps of gas that we can't directly observe, there still isn't nearly enough material to keep the Sun in a steady orbit. If there was no additional source of mass, the Sun's current speed should have assured that it would have been completely ejected from the Milky Way billions of years ago. But yet the Sun is still here, still orbiting, chained to the Milky Way by some invisible form of matter. Dark matter that lends its weight to the galaxy and glues everything together. In addition to its orbit around the center, the Sun also lazily bobs up and down like a buoy in a dark ocean, a byproduct of the unstable gravitational influences of all its neighbors. Over the course of millions of years, the Sun rises thousands of light years above the galactic plane before plunging through it, reaching a minimum and starting the cycle anew. Currently, the Sun is plunging through a region known as the local bubble, a cavity blown out of the interstellar medium by a supernova detonation that went off millions of years ago. This bubble has a density less than 1/10 the average for the Milky Way, which is already low enough that it would register as a vacuum in a laboratory on Earth. Our solar system entered the bubble somewhere between 5 and 10 million years ago, and will continue to cross its 1,000 light-year expanse for millions of years to come. And yet that is far from the end of it. For against the backdrop of the expansion of the universe, our galaxy is also on the move, and it's headed right for our nearest neighbor. Billions of years from now, our sky will be unrecognizable. The moon will be smaller, fainter, and more distant. The sun will be larger and brighter. All the familiar constellations will be gone, replaced with a new generation of stars in our solar neighborhood. And in that nighttime sky, one singular object will reign supreme, greater in majesty than any nebula, star, or planet. the Andromeda Galaxy. Right now, Andromeda is large, but not noticeably so, taking up as much of the sky as a fist held at arm's length. Within 2.5 billion years, however, Andromeda will dominate our nights, almost completely filling the sky. And it will not look like the Andromeda that we know today. In the far future, it will be distorted, its previously simple shape twisted by tremendous forces of gravity as it begins to entangle with the Milky Way. A billion years after that, the sky-filling Andromeda will be ablaze with giant stars, as the gravitational interactions between the two galaxies will ignite a new round of star formation. And it will be billions of years after that, long after our Sun has breathed its last, that the merger process between Andromeda and the Milky Way will end. The core of this new galaxy will glow with ghostly prominence in the sky, brighter than any other nighttime object. If our planet survives huddled against the meager glow of our Sun's white dwarf, we will see the sky slowly fade, first into redness, and then finally, as the last of the visible stars disappear, into blackness. It was in the 1920s that Edwin Hubble made the remarkable discovery that the Andromeda Nebula, which had long befuddled astronomers, was actually an island universe in its own right, an entire galaxy sitting 2.5 million light-years away, over 10 times more distant than the furthest object astronomers had hypothesized could exist. But measuring the speed of Andromeda was not a straightforward exercise. Andromeda is simply too big. Training a telescope on it only revealed a small portion, with wildly different velocity measurements. And so it took until 1957 for the Dutch astronomer Hendrik van der Hulst to finally provide a robust number. He examined the faint radiation emitted by neutral hydrogen, something known as 21 centimeter radiation. With careful radio measurements, astronomers like van der Hulst could build up crude maps of the feeble signal sent out by this neutral hydrogen, and examine any shifts in its spectrum. A red shift from the expected wavelength would indicate movement away from us, while a blue shift would signal motion towards us. And it was via this method that van der Hulst arrived at an average speed of minus 296 kilometers per second, with an uncertainty of around 10 kilometers, a clear indication that Andromeda is moving towards us. But to further complicate matters, that measurement didn't just include the motion of our galaxies moving together, but also the movement of the Sun around the galactic center. That must be subtracted to give the true galactic motion, and that number is right around 100 kilometers per second. But of course, now that we know the number, there is freedom to choose the frame of reference. We could say that the Milky Way is still, and that Andromeda is racing towards us, or that the Milky Way is rushing towards it at a great speed. But in the frame of reference that respects the expansion of the universe, our two galaxies are actually both moving towards each other, heading towards a common gravitational center. But this motion didn't necessarily mean that we would definitely collide. Astronomers can typically only measure the radial motion of a galaxy, the component of its velocity that is pointing either towards us or away from us. Lateral, or side-to-side motion is much more difficult to measure. Indeed, it wasn't until 2012, when a team of astronomers led by Sangmo Sohn used the Hubble Space Telescope to measure the velocities of thousands of stars within Andromeda, that we had our first clear picture of its true three-dimensional course. And it was then that we realized we really were on a collision course. The fun begins in as little as 2 billion years. As our galaxies draw closer, their immense gravitational interactions will begin to distort and reshape them. The cause is the same physics that governs the ocean tides on the Earth. The parts of each galaxy that are nearest to each other will receive a stronger gravitational pull than the rest, while the parts on the opposite sides will receive the weakest gravitational pull. This causes a tidal force that will stretch each galaxy. Sometimes entire spiral arms can detach from a galaxy, causing a phenomenon known as a tidal tail, an expanse of intense star formation stretching tens of thousands of light-years. And between the galaxies, a bridge of gas and stars often develops, as if the galaxies are reaching for each other. But when the merger event finally happens in roughly 5 billion years, it will not be like a sudden car crash. Most of the volume of each galaxy is nearly empty space, consisting of nothing more than a thin spread of plasma stretched between the stars. While the gas tangles up on itself, forming shock fronts and complex waves of disturbances, the stars simply pass by each other like two giant swarms of bees. But that doesn't mean that the stars will go unharmed. In the midst of a galaxy merger, stars will come dangerously close to each other, not enough to pair off and merge together, but more than close enough to disrupt their orbits. In short, everything will become chaos, the flat plane of the galactic disks replaced with a tangled mess of complex, overlapping orbits. Most stars will survive in this new reality, but some will be scattered, receiving boosts of energy from nearby encounters, flung away from their galactic homes forever. The first merger pass will take more than 100 million years to complete and will repeat several times over a few 100 million years, with each cycle of collision, interaction, and separation growing progressively shorter. Indeed, each one of these interactions will lead to a fresh round of star formation as gas compresses and fragments. At its peak, the star formation process in the merged galaxy could reach over 1,000 times its present-day rate. And so, for a brief moment, it will be beautiful. The merged galaxy adorned with millions of newborn stars, blazing bright white and blue, a dazzling release of the titanic energies that powered the collision. But then, sadly, comes the tragic end. Galaxies have only a limited supply of gas to turn into new generations of stars. Left alone, a galaxy like the Milky Way can steadily sip on its reserves for over 100 billion years. But the act of the collision burns far too hot, quickly depleting reservoir after reservoir of gas in the intense rounds of star formation. Once those stars burn out, there will be relatively little left to form new ones, and the only remaining stars within the galaxy will be the long-lived dwarf stars, small and dim and red. The merged galaxy, some astronomers call it Milkomeda, will become a giant elliptical, a large red ovoid incapable of substantial star formation and doomed to simply pass the days watching its population of stars drop, one by one. Of course, this is all hypothetical, our best guess as to how this massive event will unfold, and some of the most recent simulations have raised the possibility that it may not happen for another 8 billion years, if at all. Astronomers can't watch galaxy mergers play out in real time, as the process takes hundreds of millions of years to complete. Instead, what we have are snapshots, the beginning of a merger here or the end result there, a kaleidoscope of catastrophes caught in this specific moment in time. Take the Mice galaxies, a pair of interacting galaxies sitting 290 million light-years away. So named because their long tidal tails make them look like two mice nestled together, the galaxies have just begun the merger process and the ensuing gravitational distortions. And in 2023, astronomers used the James Webb Space Telescope to observe ARP 220, a pair of galaxies caught mid-merger sitting 250 million light-years away. The merger triggered a round of star formation so intense that the galaxy now shines over 100 times brighter than the Milky Way. But already star formation has shut off. What we are currently seeing is the afterglow of the already ignited stars. Throughout the universe, astronomers see countless galaxies interacting in a variety of different ways. There are galaxies colliding head-on, and others just glancing by each other. Sometimes they are perpendicular, and sometimes they are slamming their spiral arms against each other. Sometimes more than two are caught in a struggle for gravitational dominance. And so, the process of galaxy mergers began billions of years ago, even before the galaxies themselves arose, and it will continue long into the future. For the journey of the Milky Way does not end in its merger with Andromeda. Our motion through the universe is far from over. and it's towards a direction that we barely understand. Sometimes mathematics can be a crystal ball that lets the careful observer peer through the distant reaches of space and time, and sometimes that crystal ball begins its own story in a space and time far, far removed from modern-day cosmology. Take the wide-reaching consequences of the work of the French mathematician Gaspard Monge, although he didn't know it at the time. Instead, as Minister of the Navy in revolutionary France in 1792, he was more interested in working out optimization problems in the transportation of goods. Several decades later, the great pioneer André-Marie Ampère took Monge's work and expanded on it, generating an equation that has since found use in a variety of economic settings, for example in figuring out the most efficient way to move resources between mines and factories. And in the midst of World War II, the Soviet mathematician Leonid Kantorovich took the work of Monge and Ampère to the next level, extending and applying their equations to the thorny logistical problems faced by the Soviet war machine. But finally, in a beautiful example of the universality of physics, in the 1970s, Canadian-American cosmologist Jim Peebles realized that the same equations could be used to describe the efficient movement of mass in the assembly and formation of galaxies. Coming from a humble background, the son of a grain exchange worker and a homemaker, Jim would go on to study at Princeton University and eventually become a giant in the field of cosmology, though in the early days of his research in the 1960s, cosmology was not widely considered a serious field of study. We knew that the universe was expanding and that the Big Bang picture was likely correct, but there was so little observational data available that most astronomers considered the field a dead end with no serious future. But Jim pushed on and pioneered almost every aspect of modern physical cosmology, from the growth of structure to the earliest moments of the Big Bang, work that would earn him a Nobel Prize in Physics in 2019. And completing the circle, it was two astronomers, the French Roya Mahayai and the Russian Andrei Sobolevsky, who followed up on Jim's pioneering work and finally turned the so-called Monge-Ampère-Kantorovich equations into a cosmological crystal ball. They found that they could take the present-day positions of galaxies and combine that with limited information on their velocities to transport these galaxies back in time. The trick behind this approach is that we know how galaxies move. They are influenced by their mutual gravitational attraction, and we know how gravity works. So this technique allows cosmologists to take the current state of a collection of galaxies and compute where they should have been in the past. It's not perfect by any means. Every step backwards in time introduces ever larger uncertainties, and the technique can't go all the way back to the Big Bang, but it does work. With this method, Brent Tully, who first identified the beginnings of the Great Attractor, and his collaborators have released continuously updated catalogues called cosmic flows, which map out tens of thousands of galaxies around the Milky Way, along with their positions billions of years ago. This information allows him and his colleagues to reconstruct the motions of galaxies through cosmic time, not just into the past, but into the future, giving them the ability to predict where the Milky Way is headed. And it's through this technique, a combination of intense, careful observations and clever mathematical crystal balls, that we can finally understand the shape and influence of the Great Attractor and what our ultimate fate in the universe will be. The expansion of the universe allows us to construct a preferred frame of reference from which we can judge all motion, its movement relative to the general expansion flow. We can therefore create detailed velocity maps of nearby galaxies to attempt to ascertain that general flow, a laborious and error-prone exercise. However, thankfully, the universe itself gives us a snapshot of that cosmological reference frame. For confirmation of the Great Attractor's existence came not from maps of local galaxies, but from the ultimate source of light in the entire universe, the cosmic microwave background. The CMB was generated when the universe was roughly 380,000 years old, when the transition from a hot, dense plasma into a slightly less hot but neutral gas flooded the cosmos with radiation. That radiation has two very useful properties. One, it's literally everywhere. Every single cubic centimeter of space participated in the creation of the CMB, and the formation of the CMB was relatively brief, on the order of 10,000 years. So the CMB is responsible for the vast majority of photons in the universe, and we can see it in all directions in the sky. Everywhere you go in the universe, you'll always see the CMB. And secondly, the CMB is almost perfectly uniform, with deviations in temperature no bigger than roughly 1 part in a million, a reflection of the nearly pure homogeneity of the early universe. This means that we are surrounded on all sides by radiation that is almost perfectly smooth and was created in a singular moment in the distant past. It is a measurable snapshot of the cosmological reference frame. Any movement within the universe relative to that frame will distort our image of the CMB. It will appear blue-shifted in our direction of motion and red-shifted away from our direction of motion. And that's exactly what we observe. The CMB is hotter by about 0.0035 Kelvin in the direction of the constellation Leo, and colder by that same amount in the direction of the constellation Aquarius. The only way to explain this temperature discrepancy, known as a dipole, is by our motion relative to the CMB, and hence cosmological frame of reference. To get this measured shifting, our speed must be somewhere around 600 kilometers per second. Of course, some portion of that velocity is due to the Sun's orbit around the center of the Milky Way, and some is due to our inevitable collision with Andromeda. But even after subtracting that, there's still a residue, about 300 kilometers per second, and the direction of that movement, after accounting for the orbit of the Sun and the merger path of the Milky Way, is straight towards the Great Attractor. The grand structures of our universe are built from billions of years of restless, ceaseless motion. The Milky Way started out small, just a few thousand stars huddled together in the dark, but it was birthed in movement, and through successive mergers amassed itself to its present-day status. This same story has played out trillions of times across the visible universe, creating galaxy after galaxy. This is the story of hierarchical structure formation, how our universe built itself like a towering Lego masterpiece, brick by solitary brick. And so there are hierarchies of structure in the universe, galaxies, groups, clusters, and superclusters. And along with that hierarchy of structure comes a hierarchy of movement. The galaxies are already assembled from countless mergers in the past. Groups like the local group that contains the Milky Way, Andromeda, Triangulum, and a host of smaller dwarf galaxies are still in the process of collapse and merger. Indeed, roughly 100 billion years after the Milky Way and Andromeda meet each other, the other members of the local group will collapse in with them, forming a single megagalaxy. These groups of galaxies, like the local group, are in motion as well, trekking along through the expanses of the universe towards their local centers of gravitational attraction, the clusters of galaxies. The nearest cluster to us is the Virgo cluster, already home to thousands of galaxies and drawing tens of thousands more towards it. In addition to the motion of the Milky Way towards Andromeda, as a group, we are also falling towards Virgo. This process was set in motion during the earliest moments of the Big Bang, but only ramped up a few billion years ago. As clusters like Virgo grew, they exerted more gravitational influence on their surroundings. This pulled more material onto them, which increased their mass and increased their gravity. Long ago, the nascent Virgo cluster started weakly tugging on the local group, and as the cluster grew, that gentle tug turned into a mighty force. And this growth through gravity does not just stop at the scale of clusters, though clusters are the largest gravitationally bound structures in the universe. For the clusters themselves participate in yet another level of growth, one that is not quite finished: the building of superclusters. superclusters have always had a loose definition in astronomy, usually referring to anything vaguely resembling a coherent structure on scales larger than clusters. As far back as 1863, astronomers William and John Herschel noted an excess number of nebulae, which were really galaxies, in the direction of the Virgo cluster. In the 1950s, the astronomer Gérard de Vaucouleurs tentatively identified this excess of galaxies as a structure in its own right, calling it the local supergalaxy, which he later changed to local supercluster. But because superclusters are not yet fully assembled, they have no easily defined limits or boundaries. Initially, astronomers believed that the Virgo cluster sat at the heart of the local supercluster, also confusingly known as the Virgo supercluster, a rough collection of around 100 galaxy groups and individual clusters spanning over 100 million light-years in breadth. But beginning in 2014, Brent Tully, along with collaborators Hélène Courtois, Yehuda Hoffman, and Daniel Pomered, proposed a new definition of supercluster. This definition was not based on spatial extent, but on movement. They employed the Monge-Ampère-Kantorovich reconstruction technique to spring their galaxy surveys into life, changing them from static snapshots of the present-day universe into living entities, enabling them to see where these tens of thousands of galaxies near to us came from and discern where they're going. And it was the motions of these galaxies that revealed the true extent of our local supercluster. It turned out what we thought was a supercluster was just a single branch, one of 4 of a much larger assemblage, an entity that Tully and his collaborators named Laniakea, a Hawaiian word that roughly translates to immense heaven or open skies. And so the Milky Way galaxy belongs to the local group because we are all moving towards a common center, which will eventually become a gigantic singular galaxy. The local group belongs to the Virgo branch of our supercluster because we are all headed towards the Virgo cluster. And the Virgo supercluster branch belongs to Laniakea because we are all moving towards the center of Laniakea. 100,000 galaxies in total, spanning across over 500 million light-years in length, assembled on 4 separate branches, each one considered superclusters in their own right, all headed for a single destination: the beating heart of Laniakea, the local center of attraction of this portion of the universe, the final assembly point of a construction process that began billions of years ago and will take hundreds of billions of years to complete. The center of it all. The Great Attractor. Our portrait of the Great Attractor is hazy at best, because it lies within the zone of avoidance, the direction in the universe obscured by our own galaxy's dust. But some wavelengths of light can penetrate that dust, and surveys taken with radio, infrared, and X-ray have shown us glimpses of what lies beyond the veil, and what might be sitting within the Great Attractor's region. As best we can tell, the heart of Laniakea, the focal point for the great migration of 100,000 galaxies including the Milky Way, is the Norma cluster, named for the constellation we must peer through to see it. It is several times larger than a typical galaxy cluster, and sits about 220 million light-years away from us, and so even at a speed of over 100 kilometers per second, the Norma cluster is so far away that our journey towards it would take over 100 billion years. Norma began life just like any other galaxy cluster, the result of countless mergers and relentless gravitational attraction. But it happened to sit at the bottom of an immense gravitational well, the single point of attraction for this entire local region of the universe. Indeed, over time, Norma will only grow more immense as it continues to collect more material within it. But recent surveys, again using the Monge-Ampère-Kantorovich reconstruction technique, have revealed that our motion towards the Great Attractor, that is, the Norma cluster, is still not the end of the story. For one, even though our understanding of Norma is vague at best, it appears to be a little too small. Even adding in the contribution of its dark matter, Norma's gravitational pull is not quite large enough to account for the speed with which we are moving towards the Great Attractor. In other words, the Great Attractor isn't quite as great as it initially appeared. There seems to be an additional source of attraction sitting even further beyond the Norma cluster, for Norma too appears to be in motion. An entity even larger, even greater than the Great Attractor, sitting over 650 million light-years away. The structure was first observed by Harlow Shapley of the Harvard College Observatory in 1930, who could only dimly perceive a distant nebulosity. But we now know it to be another supercluster, the next nearest neighbor to our own Laniakea, and from what we can tell, it's a supercluster even larger than our own. The incredible mass of the Shapley supercluster is influencing every galaxy, every group, and every cluster around it for hundreds of millions of light-years. Indeed, if we were to give the universe enough time, and for all this motion to continue unabated, the Laniakea would transform into a single compact object, a much more immense version of the Norma cluster that currently sits at its heart, and that object would eventually make its way to a similar one, situated at the center of the Shapley supercluster. And there are even hints of additional motion on even greater scales. In 2008, NASA astronomer Alexander Kashlinsky was observing a subtle signal found in the cosmic microwave background. Known as the kinematic Sanyaev-Zeldovich effect, it's a tiny imprint caused when light from the CMB passes through a galaxy cluster on its way towards us. By comparing these signals in different regions of the sky, Kashlinsky found that there appeared to be a large flow of clusters towards a direction on our sky between the constellations Centaurus and Vela. This apparent dark flow, as Kashlinsky nicknamed it, was between 600 and 1,000 kilometers per second, faster than our own motion towards the Great Attractor, and that motion caught up a significant portion of clusters in the universe. And the intriguing puzzle with this dark flow is that the differences in density in the universe aren't large enough to explain the velocity. There simply isn't enough material collected together in any one patch of the universe to explain such large-scale, coherent motion. Although, in 2013, scientists with the ESA's Planck satellite found no evidence for dark flow, debate continues. Whether this dark flow is a real feature of our cosmos or not, there are still reverberations echoing from the distant past. When the universe was only a few 100,000 years old, it was over 1 million times smaller than it is today, and all its material was compressed into a hot, dense plasma. Like any plasma, sound waves crashed and echoed within it as waves of density surged back and forth. And these sound waves have a name: baryonic acoustic oscillations. When the universe expanded and cooled, it transitioned from a plasma to a neutral gas, releasing the cosmic microwave background. And at that moment, the baryonic acoustic oscillations were frozen in place, trapped in whatever position and state they were in when the plasma dissipated. These oscillations persisted as tiny fluctuations in density, a series of overlapping shells of slightly higher density than their surroundings. Over time, along with the rest of the universe, they grew, accumulating more matter than average, and after hundreds of millions of years, more galaxies than average. And today, cosmologists map the imprint of the acoustic oscillations in massive surveys of galaxies, using them to test models of the history of the universe. And in 2023, Brent Tully, Cullen Howlett, and Daniel Pomered discovered that many nearby clusters, walls, and other structures of the cosmic web are arranged in the shape of a shell. The radius of this shell is over 400 million light-years, and it includes elements like the Sloan Great Wall, the CFA Great Wall, and the Hercules Complex, all centered on the Boötes supercluster, all enormous entities in their own right. Tully and his collaborators believe that this structure is an individual baryonic acoustic oscillation, a remnant of the chaotic plasma era of the universe, still echoing today. Appropriately enough, they named it Ho'olelana, taken from a portion of a Hawaiian creation chant, meaning from deep darkness came murmurs of awakening. And finally, reverberations of ages past are not the only forces at play in the deep universe. We are constantly pulled by gravity. The gravity of Andromeda, the gravity of the Virgo cluster, the gravity of the Great Attractor, the gravity of the Shapley supercluster, the gravity of Ho'olilana. But there are also pushes, sources not of attraction, but of repulsion. Adding up all the known sources of mass in the wider universe, as deep and as far as our galaxy surveys will reveal to us, is still not enough to fully account for the motion of the Milky Way galaxy. There appears to be something else, something on the opposite side of the sky of the Shapley supercluster, something that we have not yet fully mapped or understood. A great void, a vast expanse of nothingness, one of many that dominate the volume of the universe. Named the Dipole-Repeller Void, we do not yet have an accurate understanding of its shape, size, or dimensions. All we know is that it seems to participate in the great movements that define life in the large-scale universe. And the important thing to realize here is that these great voids don't just let go of matter. They actively push away the galaxies at their edges, because despite their emptiness, they are filled to the brim with dark energy. And eventually, the repulsion of these voids will unwind the cosmic clock, unravel the cosmic web, and prevent us from ever reaching the Great Attractor. It was perhaps the only time that Einstein didn't trust his own mathematics. Early in his career, he had made a name for himself with his leaps of imagination and insight, grounded in a deep understanding of the physical universe and the mathematics needed to bring his ideas to light. Indeed, in a single year, he crafted the special theory of relativity, discovered a foundational principle of quantum mechanics, and conclusively demonstrated the existence of atoms. But in 1917, Einstein tripped over himself. He had just developed general relativity and found numerous applications for it, and so had decided to take these newfound equations and use them to describe the entire universe. After all, gravity is the only force that operates at large scales across all objects, and so the language of general relativity should have been more than capable of describing the evolution of the cosmos. Yet what he found surprised him. His equations naturally predicted a dynamic universe, one that was always in motion, with all objects at large scales either collapsing together or expanding away from each other. This went against the conventional wisdom at the time that while planets may orbit and stars may move here and there, the large-scale universe was fixed and static for all eternity. And so, for whatever reason, Einstein didn't want to disrupt the established order, and he found an opportunity in the form of a cosmological constant, a number that he could slip into his equations without breaking them. In the solar system, this cosmological constant didn't affect any measurements, but on large scales, it would act to stabilize the universe, overcoming the natural tendency of objects in the cosmos to move. Unfortunately for this idea, just a few years later, Edwin Hubble would discover the expansion of the universe. While Einstein never admitted it, in public or in any letter, his closest friends recalled that he would refer to the cosmological constant as his greatest blunder. Yet despite Einstein's regret, the constant never quite went away. Eventually, the great Soviet astrophysicist Yakov Zeldovich recognized its importance when he equated the cosmological constant to the vacuum energy of space-time, just two different expressions of the same fundamental concept. And in 1998, astronomers realized that the expansion of the universe was accelerating. The most likely culprit for this mysterious accelerated expansion? The vacuum energy of space-time. And so in the span of only a few weeks, cosmologists around the world dusted off their history books and reacquainted themselves with Einstein's greatest blunder, and how that little innocent term in the equations just might be tearing the universe apart. The local group, the Virgo cluster, the Laniakea supercluster, they were all built atom by atom, galaxy by galaxy. They took billions of years of slow and steady movement to reach their current stunning grandeur. While the rest of the universe may be continually getting bigger, and galaxies gently drifting away with the Hubble flow, the galaxies of Laniakea should always have been able to call it home. Until dark energy tipped the balance. For 5 billion years ago, the expansion of the universe diluted all its matter to a point where a new force could emerge triumphant. That force was always there, waiting in the shadows, part of the very fabric of space-time. But it was weak, and so it sat in the background, content to let the forces of radiation and matter dominate the evolution of the cosmos, until its time finally came. We still don't definitively understand what dark energy is. We merely know what it's doing. It's causing the expansion of the universe to accelerate. And its influence is only growing. As the universe expands, its matter contents get more and more spread out. But that same expansion creates more dark energy. Whatever it is, it appears to be related to the vacuum energy of space-time. If you have a completely empty box, devoid of all matter and radiation, you are left with nothing but vacuum. But quantum mechanics tells us that that vacuum is alive, a roiling, bubbling sea of fundamental particles constantly vibrating in and out of existence. And dark energy appears to be a manifestation of that vacuum energy. As the universe expands, there's more empty space, more vacuum, and so, more dark energy. "5 billion years ago was the turnover point when the density of matter dropped for the first time below the density of dark energy. And since then, it's only gotten worse. At the present epoch, dark energy accounts for roughly 70% of all the contents of the universe. In the future, it will be 90%, then 99%, then even more, building up on itself as the universe continues to expand. And as that expansion accelerates, it only drives the creation of more dark energy, a process that has no apparent end and shows no sign of slowing down. Dark energy will not let the universe come to rest, and it's already begun its process of deconstruction in the voids. The voids of our universe are by definition almost entirely empty of matter. Only the occasional thin filament of ionized gas or small dwarf galaxy. They are almost entirely pure vacuum, which means that they are filled with dark energy and driven to expand by the repulsive effects of that dark force. The voids are therefore the precise locations within the universe where the accelerated expansion takes place. As time goes on, the voids will only get bigger and merge, driving the galaxies at their edges away from each other faster than their gravitational attraction can keep them together. The only objects that will survive the growing darkness will be those that are already gravitationally bound. This means that our local group will survive, although transformed as its individual member galaxies coalesce. And it means that clusters like Virgo will also survive, safe harbors for the thousands of galaxies that already call it home. But the superclusters will not make it. Laniakea, Shapley, and all the millions of others that twist and wind their way to create the backbone of the cosmic web will not maintain their cohesion. It is simply too late. They simply did not have time to pull themselves close enough together before the forces of dark energy began their work 5 billion years ago. And finally, we will never complete our journey. The Milky Way will continue on its tragic course with Andromeda, but the local group will never make it to the safe shores of the Virgo cluster, let alone the Great Attractor or whatever lies beyond. Billions of years from now, our passage through space towards the Great Attractor will slow down, stop, and reverse. Over the course of hundreds of billions of years, we will see those distant clusters and galaxies dim and fade from view, eventually slipping over our cosmological horizon, caught up in the accelerated expansion driven by dark energy. Indeed, after a long enough time, trillions of years from now, the mega-galaxy that was once the local group will be isolated, adrift in a sea of nothingness, as every other galaxy slips away. But even then, our motion will not cease. Gravitational interactions within the future galaxy will cause stars to randomly scatter away, and once they slip outside its embrace, they too will be caught up in the accelerated expansion, flung away as if they were never there. One by one, star by star, our galaxy will diminish. The same fate will apply to every macroscopic object. Hundreds of trillions of years from now, each individual body will be completely and utterly isolated from everything else in the universe, separated by vast gulfs of faster-than-light expansion. And so, with nothing left in the wider universe, with no outside frames of reference, with no stars to gauge motion against or Hubble flows to compare to, with no other sources of attraction or repulsion, the universe, what's left of it, will finally come to rest. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.